Hey everyone, welcome to another QualQuest video. So today I thought I would take a question from one of our linear algebra questions. So we're given this matrix, this 3x3 matrix of numbers. Basically what we have to find is the determinant of e to the at, where t is some number. And for exponents of a matrix, e to a power, it's very much like this Taylor series for a polynomial. Or for it's like the Taylor expansion for a single value. So you would have 1 plus x squared over 2 plus etc., x to the n over n factorial. But instead of n, or whatever your number is, we're plugging in at in for each of these. So that's the definition of the e to a matrix. But so how the heck do we find the determinant of that thing? I mean, these are not nice numbers. And, there's no way we're going to be able to easily compute at to the n for very large powers of n. So, what can we do? So, in order to help try and figure this out, first we're going to have to recall a single thing to help us organize this thing and see if our matrix is diagonalizable. Basically, if the original determinant A is not equal to 0, then we can rewrite our matrix A as some matrix T times some diagonal matrix capital lambda times T inverse, where basically lambda is a diagonal matrix containing the eigenvalues of A along its main principal diagonal. And we're doing a little bit of quick hand computation. It turns out the determinant of A is 66 and not 0, so we're okay and we can compute this part here. Actually, let me really quickly change our t's to u's. You might see why in a little bit. Alright, now plugging in our diagonalizable version into our e to the at formula. So we plug in u lambda u inverse in for a, and then we'll carry out the t's just to the side because they are part of the equation, but they're just multiplicative values, so we can just pull those off at the side. Another quick substitution I really did here quickly was I added u and u inverse to the front of I, because u times u inverse is just I. So we're totally fine with that. So basically what will happen is, once we have higher powers of A, all the u inverses and u's on the inside will cancel out. So you'll just have one u on the left side, one u inverse on the right side, and just a bunch of lambdas in the middle. Along with our t to our powers. So basically, this is going to rewrite as u times our exponential matrix form of e to the lambda t times u inverse. After doing just some quick notation here, we wanted to find the original determinant of our entire system. So if we take the determinant of a product of matrices, that's the same as the product of the determinants of each matrix. So fortunately now we can group u and u inverse together on one side. We'll just have 1, which is good because u times u inverse is the identity matrix, and all we're left with now is the determinant of e to the lambda t. And thus, I'm just rewriting our e to the lambda t in our original matrix form, where we have lambda 1, lambda 2, and lambda 3, which are the eigenvalues of the original matrix A. So again, this is why it's nice to have it in diagonalizable form, because that way we don't have to worry about all these other numbers. They just stay 0 the entire time. And basically we can then take the exponent individually of each part. So then to find the determinant of the whole thing, we have to basically multiply these three values together. So we have e to the lambda 1t times e to the lambda 2t times e to the lambda 3t. We can organize our sums together, but now what? So now for our last step of this problem, we're going to have to recall one awesome fact. It turns out that for a given matrix A, the sum of its eigenvalues is exactly the same as the sum of its diagonal entries at the beginning. So this is also known as the trace of the matrix. So basically, if we wanted to find our lambda 1, lambda 2, and lambda 3, find the sum of those, we just need to look back at the original matrix A. So, and add up the sum of its diagonal entries. So we have 1 minus 4 plus 3, 0. Thus, we know that the sum of our eigenvalues is also 0. And thus, getting back to our original question, the determinant of e to the at, we know that it's e to the t times the sum of the zeros, or times the sum of the lambdas, which is 0. So it's e to the 0, which is 1. So actually, it doesn't matter what time it is as it evolves over t. The determinant is always 1. Big Mac saying, later.